Okay, we're gonna start now. Welcome back, everyone. Hopefully, you had a really good week. Today, we're going to learn about Pascal's triangle. And you're probably wondering, like, why I called like this entire slideshow Pascal's triangle instead of like something general like combinatorics or like geometry or something. And you'll see. It says 31st. I think. I don't know why. I'll change it up. Okay, I'll say November 21st. Not sure why it says that. Probably because I copy pasted this template from like another lesson. So yeah, I forgot to change that date. There you go. Should stop bothering you now. Okay. So we're gonna learn about Pascal's triangle, and some of you have probably seen this already. So it's a triangle that looks like this. So you have like a bunch of ones on the side, and then in the middle you have a bunch of numbers. Oh, okay. Now we have full class. Hello, Yvonne. So I did 2D attendance. It's full class. Haven't had that in a while, so that's good. Okay, so today we're going to look at Pascal's triangle, and you see that a number inside Pascal's triangle is obtained by the sum of the two numbers above it. So let's pick an example. Let's look at 6 right here, the middle 6. So 6 is the sum of the numbers on top of it. So 3 plus 3. Could look at 15 right here. Let me get a pointer. 15 right here. 15 is equal to 10 plus 5. And then you repeat this pattern I repeat this for all of the numbers in Pascal triangle. Aside from the ones will always stay on the leftmost side or the rightmost side. It'll always be a 1. And there are various applications of Pascal's triangle, but we're going to look at one specifically. And so remember last week we talked about combinatorics. This week we're still going to continue with some combinatorics. So let's look at how Pascal's triangle is related with that topic. So if we can see in this picture over here, we see that each number in Pascal's triangle can be expressed using choose notation. And if you remember choose notation from last week, it looks like this. So n choose k is equal to this fraction right here. And for this choose notation, we have n equal to the row number. So n is the top number in the choose notation. This is equal to the row number. So we look at example like right here. This actually starts, so for the Pascal triangle, we actually start with row 0. And same thing for the column, we actually start the columns on 0. So we're doing 0 indexing right here. So, and the k so the bottom number is equal to the column number. We can choose an example. So this is 0th row, 0th column, or 0, 0. For how about 3, 0? So this is the third row. So 0, 1, 2, 3, the third row. And this is also the first column, but we call it the 0th column because we're starting on 0. Choose 4, 3. So this is 0, 1, 2, 3, 4. This is considered row number 4. You can also call it the 5th row. And then it's like the 4th column from the left, but it's called column number 3 because we're starting on 0. 0, 1, 2, 3. And these numbers all match with the numbers on the Pascal's triangle. So let's see, 4 choose 3 should be equal to 4. We can check it out with what we have on the Pascal's triangle. So 0, 1, 2, 3, 4. 0, 1, 2, 3. So here's 4. This is 4 choose 3 right here. You see how it matches with this number. Are there any questions about this so far? No questions? Okay, let's move on. So from the Pascal's triangle, so from this Pascal's triangle in particular, like the triangle with the n choose k notation, we can come up with many different properties. So we're going to look at some Pascal triangle properties in the next few slides. Okay. So here's the first property. So you notice that in a row of Pascal's triangle, some numbers are equal to each other. So let's choose the 5th row or the 6th row right here. 1, 5, 10, 10, 5, 1. You can see that numbers 1, 5, and 10 are repeated. And so what do these numbers have in common? This property. We have n choose r is equal to n choose n minus r. Here's an example. So we have 5 choose 2 is equal to 5 choose 5 minus 2. 5 minus 2 is equal to 3. So 5 choose 2 is equal to 5 choose 3. And 5 choose 2 and 5 choose 3 should be both equal to 10. Actually, yeah, 10, I believe. These are both equal to 10. Are there any questions about this property? No questions? It's also fairly simple to prove as well. I can show you how. But we also covered this last week, just like briefly. So say we have n choose r, and choose n minus r. So we can write this out in a fraction, right? So we have n factorial up here. We also have r factorial. And also in the denominator, we have n minus r factorial. Now let's try this one. So we have on the top n factorial. This time we're starting with n minus r factorial. But you'll see why that doesn't really matter. So we have n minus r factorial. And for here we have n minus n plus r. So I did n minus in brackets n minus r, just expanded that out. And this would just be equal to this. So the n minus n plus r would just become r factorial. And so the terms in the denominator for these two expressions, so they're in different spots. So like n minus r factorial, we have it first. Here we have r factorial last, but that doesn't matter in a product, right? That doesn't really matter if we switch the order of the numbers or not, because it'll just become the same. It'll just become the same product. So now we prove. So here we prove that these two expressions are equal to each other, just like that. Let's go back to the slideshow. Or just wait a sec. All right. Okay, let's look at the next property. We have binomial coefficients. So what is this? So we know that in the Pascal's triangle, like how we construct it, we have two numbers on the top that add together to get a number below it, like in between. So then we can express this using a formula. And here's the formula. We have n choose k. Remember that n is the row number and k is the column number. N choose k plus n choose k plus 1. So we increase the column number by 1. That's how we got that. And these two expressions add together gives you n plus 1 choose k plus 1. So here you're increasing the row number. So remember, two numbers in one row, in the same row, and you add up to get the number in the row below. So you're increasing the row number by 1, and you're also increasing the column number by 1, or it's the same over here. So n choose 1, n plus 1 choose k plus 1. And here you can see some examples. So we have 1, 2 over here. 1 and 2 make 3. So we try to find that over here. So the 1 over here corresponds to 2 choose 0. 2 would correspond to 2 choose 1. 2 choose 0 plus 2 choose 1 would equal 3 choose 1. And this matches the property over here. Are there any questions? No questions? It is, yeah. Remember that we're starting rows and columns on 0. Yep, no worries. Yeah. So remember, starting the row number and the column numbers on 0, and those are 0 are basically like equal to 1. So these numbers over here are just the ones on the left side. These numbers are here, the ones on the right side. So that, yeah. I chose these two pictures from like two different sources, so like they might not necessarily like match like row number wise, but you can still see how to correlate. Oh, Jerry had a question. What is this formula for? Oh, this formula is just one of the properties of the Pascal's triangle that you notice. So remember that each number in the Pascal's triangle is the sum of the two numbers on top of it, and then we can use that with the combinatorics form of Pascal's triangle to get this property right here. So this is just to simplify like this sum right here. So if you see like an n choose k and then n choose k plus 1 add together, you can just simplify it with this expression. So instead of just adding these, you have n plus 1 choose k plus 1. It'll just make your life a bit easier. So yeah. Any other questions? No questions? Okay, let's move on. Now we're going to look at another identity called the hockey stick identity, and we'll figure out why it's called a hockey stick. So say we're looking at the sum of numbers in a diagonal. So let's look at the first part. So sum of numbers in a diagonal from right to left. So we're going from right to left like this. This can be expressed with this notation. And probably a lot of you haven't seen what this notation is, and I'll show it right here. But basically you have a sum from k equal to r to n, and then you have an expression k choose r. This is equal to n plus 1 choose r plus 1. And I'll explain what this notation is. So we have this notation. It's called sigma notation. Sigma notation just means a sum or a summation. And here's a picture that helps out with this. So say we have this summation. Say we have this summation expression. On below this notation, or like the symbol, we have n equal to 1. What this represents is the initial value. And we have a number on the top of the symbol. This is 4. So 4 is the final value at which you stop at. So you're starting from n equal to 1, and you're going to n equal to 4. And then the expression, like right beside this entire symbol. So we have n right here. This just represents like what to sum. So like for each number between 1 and 4, or your bottom number and your top number, you're substituting that into the expression in yellow right here. And then you're adding all of those expressions together. So we have first, we're starting with n equal to 1. We substitute that into n, we get 1. Next we move to 2, and then 3, and then 4. And then we just add those together to get 10. Any questions about this notation? Just this notation. No, don't worry about the hockey stick identity. Worry about this notation. Any questions about this? Because it's probably like new territory. You guys haven't seen it. So I just want to make it clear for you guys. Right? I'm just going to assume you guys all understand that. That sounds good. So remember that we use a notation with this identity. We get n plus 1 choose r plus 1 for a diagonal from right to left. So like this one highlighted in blue, we have 1 plus 3 plus 6, and then we get 10 right here. And this is called a hockey stick identity just because like the pattern that you make on the Pascal's triangle kind of looks like an L shape, or like a hockey stick shape. Could have just said the L identity, but whatever. We can also express numbers in a diagonal from right to left as well. So like this way. but we rarely see that. But there is also an expression for that. So it looks like this. You have n plus k plus 1, choose k. But you don't have to worry about that because you rarely see this kind of expression in like actual math problems. So just focus on the expression at the top here. So a diagonal from right to left, just focus on this expression because we'll be seeing this in problem more often. We'll be seeing this expression more often in problems than this. So focus on this. And also just a note that diagonals, so the diagonals for which you're summing, they have to start on 1. So it have to start on like the left side or the rightmost side. But they can go for as long as they want. So say we have 136. We can also go all the way down to like 36, and we add it up, and we should get 120. You could check. You could try it out like right now, but you don't have to. It'll work. Are there any questions about this identity? I think what I'm going to do is write down. I'm going to try to expand this hockey stick identity for you guys, just to show you what it looks like. Let's go back to here. So here's what it looked like. So we have sigma notation. Below we have k equal to r. On the top here we had n. And then the expression right beside it was k choose r. And so remember that we're always, so the variable here, k, so this is a variable that we want to substitute for every single term that we have to add up. So we have to substitute k from r to n. So what this will look like, we're substituting r into k. So we have r, choose r. And this is equal to 1, by the way. And then we increase r by 1 continually until we get to n. So we have r plus 1, choose r. And then we have r plus 2, choose r. So increase r plus 1 by 1. Oops, my handwriting is kind of sloppy. Sorry. Okay, and we can continue this until we reach n. I'll write down 2 more terms. So the term right before n would be n minus 1, choose r. So just to show you that it's continued, like this pattern is always continuing. And then finally we have n choose r. And then the hockey stick identity, what it tells us is that this whole expression is equal to n plus 1, choose r plus 1. So it really simplifies this. Instead of having to add up all these terms together, we can just simplify it with this expression. So with n plus 1, choose r plus 1. And I'll just draw the arrows right here, just like, so let's say we've substituted n for 2, or like n with equal to 3, and then r is equal to 1 over here. So say n was 3, r was equal to 1, then this expression would be equal to 4 choose 2. So 3 plus 1 choose 1 plus 1. So that's a simple way you can see it. Any questions about this? No questions? Right. Hope you guys understood that. We'll be using this in a few problems later. Okay, and this is the last identity that we're going to learn. If we look at the sum of all numbers in a row, we'll notice that they're equal to powers of 2. So we can express it in like sigma notation form, like this. So we have sigma notation. Below we have k starting at 0. Yeah. Oh, sorry. Okay. Here's a slide. Sorry, I forgot to switch tabs. Okay, my bad. Here, I'll explain it again. So if you notice in a Pascal's triangle, that the sum of the numbers in a row. So we have 1, We have 1 plus 1 equal to 2. 1 plus 2 plus 1 is equal to 4. 1 plus 3 plus 3 plus 1 gives you 8. 1, 4, 6, 4, 1 would give you 16. Notice that they're all powers of 2. And we can express this using an expression, a mathematical expression as well. And this mathematical expression looks like this. We have to use sigma notation again. And we have k is starting from 0. And on the top we have n. So remember, n is the row number, k is the column number. And we're starting those on 0. And we're just adding up n choose k. So for each n choose k term, we're just increasing the column number, and then we just add those up. So k starts at 0, then it will start at 1, then it'll start and go to 2, etc., all the way to n, which would be n choose n, which is 1. So like you're going from the left side all the way to the right side. So that's how this sum works. And then this would just be equal to 2 to the exponent n, where n is the row number. Yep. Are there any questions about this? I guess a simple way just to like memorize this would be to like, so like if you're adding numbers in a row, the sum would be equal to 2 to the exponent of that row number. Remember, row numbers start at 0 over here. Oh, that's a simple way you can memorize this. Any questions? No questions, right? And the last few slides will just be a bunch of problems that we're going to solve. So here's problem number 1. So how many different combinations of 13 card hands can I choose from a deck of 52 cards? Express the answer as 2 different variants of n choose k. I'll give you guys like a minute or so to solve that. And if you want, you type your answer in the chat. Just type n choose k, something like that. So you can say like 50, like 2 choose 1. Just literally type that out in the chat, and I'll understand it. And remember, you need 2 of those. I don't know, just I think bridge is 13 card hands. I don't remember, but okay, just assume bridge, but who cares? Yeah. So yeah, just if you want to unmute yourself and like say the answer, like and choose K, go ahead, or you can type in the chat, just like that format. You don't have to find the exact value because that would be really, really big, and there's no point doing that. Does anyone have an answer? Right? Well, 2 separate answers. Yep, Chengao, you're right. So 52 choose 52 minus 13. So remember, we used the first property of Pascal's triangle, where we have equal numbers in a row. We have 52 choose, so 52 was n, r here was 13. 52 choose 52 minus 13. 52 minus 13 is equal to 39. So 52 choose 39. That's one way you can express it. What's the other way? Yeah, just 52 choose 13. That's all I got to say. So those are 2 answers. We have 52 choose 13 and 52 choose 39. And if you want to double check that, you can just add the bottom numbers in the choose notation. So you add the 13 and add the 39 together. And if those sum up to n or 52, then you got the right answer. That's one way you can double check. Any questions about this? Jerry asks why that formula, like why we use it in the question. Is that what you're asking? Okay, so remember the question asks for two different like variants of n choose k. Variants as in like changing these numbers around. And so we usually like don't really change around n because that would be like really difficult to like figure out. But we can change around k, right? So we can choose 13 cards out of 52 cards, or we can choose 39 cards out of 52 cards and put those away and then use the remaining cards as your deck. And so we use this formula to help us out to get those variants right here. Did I answer your question? All right, hopefully it did. So that's how we use that formula in this question. Let's go to question number 2, problem number 2. So what is the sum of choosing 2 people from a group of 7 people and then 3 people from the same original group of 7? So you're adding up 2 different combinations together. And you're going to have to use one of the Pascal triangle properties to simplify this. Or you don't have to. It's up to you. I'll give you guys a minute or so to figure this out. No. Out of the 7 people, you choose 3. Out of the 7 people, you also choose 2. So just sum those up. Yeah. So you just put those 2 people back after we chose them. Yeah. Okay, wait a couple more seconds. Yeah. You want on a classroom right now? Sure, I'll do it. Okay. Are you having a hard time like following it on the like Google Meet right now? Yeah, I'll post it right now. And I'll update the post just to post homework. I'll post homework, so actually. And I'll update later to post the recording. It is 21st. Okay, I'll add those links. Peace. All right, Eric, I just posted. You can check now. Okay, so we have some answers right now at 41, 336. Don't think it's any of them. Let me see that. No, it's not them. It's larger than 41. It's much smaller than 336, actually. Yeah, Kayla got it. It's 56. I'll show you guys why. Let's go back to our handy whiteboard. Again, do a drawing. Okay, so first we're choosing 2 people out of the 7 people. So can someone tell me how to express that with choose notation? Yeah, and choose R. Like, what's N and what's R? Tell me that. Oh, Jerry got it. He said 7 choose 2. Okay, and then now we're choosing 3 people out of the same 7 people. So just assume that we put the 2 people back, then we're just choosing 3 people. So can someone tell me what the expression for that is? 7 choose 3. Yeah, N is 7. You just say the number. There you go. So we have 7 choose 2 plus 7 choose 3. So we could calculate this like these 2 expressions individually. So we can just calculate 7 choose 2, and then we can just calculate 7 choose 3 and then add them together. Or we can use that Pascal triangle property. So let's go back to the slideshow. It was this one. Binomial coefficients right here. So we have 7, 2, and we have 7 choose 2 plus 1, which is 3. So that means we can use this property to simplify that expression into n plus 1 choose k plus 1. Let's go back. All right, so let's express this with 1 choose notation. Can someone tell me what should be in here? Perfect, a choose 3. So remember, n is equal to 7. We had k. I think we use r. I don't remember. my short-term memory is bad. We use k. Yeah, okay, we use k. We had k is equal to 2. And so the final answer would just be n choose 1. N plus 1 choose k plus 1. So 7 plus 1 is 8. 2 plus 1 gives us 3. And this will be our final answer. And then we could try to solve for that right here. So we have 8 factorial divided by 3 factorial times 8 minus 3 gives you 5. 5 factorial. So to expand that, 5 factorial would cancel out with the last 5 terms in the 8 factorial. Here we're left with 6 times 7 times 8. And if you calculate 3 factorial, that would give you 6. So then 3 factorial would cancel out with the 6 over here. And you're left with 7 times 8. And then 7 times 8 would give you 56. And that's your final answer. Right. Are there any questions? No questions? All right, let's move on. Problem number 3. Find the value of this summation right here. I'll give you guys a minute or so to figure out. So you're going from k equal to 2, you substitute that into the k, and we go all the way to 5 choose 2. But remember, you can just simplify this as one expression. Anyone have an answer so far? Bob says 20. 20 is correct. Alright, let's take this up. Let's go back here. Now just draw the summation out again. So we have k starting at 2, going all the way to 5. And here we have k. So we're substituting these k values into the top part. And on the bottom, we also have this value too. Sorry, sloppy handwriting. There you go. And if you want to express that, like expand that out, it'll look like this: 2 choose 2 plus 3 choose 2. So we're incrementing the k value, the top value, by 1 each time. And then we're just adding this up. 4 choose 2. Yeah, I just want to help you guys familiarize yourself with like this sum notation, so you can use it in the future. I don't think you'll learn this in high school, though. I don't know why I don't teach it. They should be teaching this, but you don't learn it, which is at SMH high schools. Hmm? You don't learn in high school. That's a bummer, but you might learn in university, but I don't know. I'm not in university yet. I'm grade 12, going to university next year. This isn't no. This is advanced stuff, yeah. Probably not, yeah. Oh yeah, and also fun fact: you do not learn combinatorics in high school. Probably surprised about that. You don't learn combinatorics in high school. This is also sad. Like this, yeah, this choose notation, all this stuff, you don't learn that in high school. It's sad. You have to like specialize it in university if you want to learn more about this. Yep. Okay, so this is what the expanded formula would look like, right? And if you add the, you could just like calculate these individually, add them up, or we could use that hockey stick identity that I taught you a few slides ago. So remember, hockey stick identity look like n plus 1 choose k plus 1, or r plus 1. So this is constant right here, and this is n right here. So this was what the hockey stick identity would let you do, just like that. So this is 6 choose 3. Let's write down right here. And then if we expand that, we have 6 factorial divided by 3 factorial, and then another 3 factorial. Okay, so 1 3 factorial would cancel out with the 3 times 2 times 1 in the 6 factorial. And we're left with 4 times 5 times 6. Realize that 3 factorial is equal to 6, so we cancel out this 3 factorial with the 6 right here. We're left with 4 times 5. 4 times 5 would give you 20. And that's your final answer. Any questions about this? No questions? Okay, let's go back to the slideshow. There's a few more problems left. We might end a bit early. We'll see. Okay, so here's another problem. Problem number 4. Excuse me? You say you want your money back? Mm-hmm. Oh, okay, that's what you said. I thought I thought you just wanted like asked you just asked if you want money back. That would have been rude, but I guess compensate for it. I guess, yeah. Well, we'll see. We'll see what happens. Right. Usually, the time is not like an issue for me personally. If I had to attend any classes, time wouldn't be an issue, like with the money issue. But yeah, here's this fourth problem. At a local library, Joe found himself interested in 10 different books. He will be satisfied if he rents out at least one of them, and assume that all the books are unique. So, how many different combinations of books can he take out in order to be satisfied? And I'll give you guys a hint. You'll have to use this property. So, sum of all numbers in a row, you'll be using that here. I'll let you guys figure that out. And if you have an answer, just type in the chat, or you can just unmute yourself, whatever you want. So just remember that. So he can choose either one book, he can choose two books, he can choose three books, and etc. etc. So we can express those as like n choose k, and you add them together, and then you can simplify it with this expression. So that's the hint. Oops, that was the next problem. That was the last problem, but there you go. Well, okay, coronavirus. No, is the library actually open right now? Like YMCA one should be open, right? Oh yeah, red zone. No, it starts Monday, so probably still is open. I guess. But yeah, but he has to take at least one book. If he takes zero books, then that's not a combination. This whole lesson was about how combinatorics is part of Pascal's triangle. So of course they're related. He can take all 10 books. I here said at least one of them, so he can take two or three or four, or all the way to 10. But he needs at least one. Anyone have an answer so far? Not quite. I'll wait a couple more seconds. Not 120. Keep trying. Just remember that it has to be close to a power of 2. That's all I do. Or it could be equal. What else? Ooh, Bob, 1024. That is really, really, really close. Yeah, you're on the right track then. You're you're actually counting one extra combination. That's all I can tell you. Assume that if he doesn't take out any books, that's also a combination. There you go. 1023. Patrick got it. Yeah, at least one. Okay, I'll show you. I'll show you why. Yeah, so if he doesn't take out any book, then that still kind of counts as a combination. But like, yes, yeah, exactly, exactly. Okay, I'll show you guys the solution. Just chill, calm down. I will show you guys why. So, as all of you said, so he can choose like one book, two books, all the way to 10 books. Well, I mentioned that, but Eric mentioned that you add up all those combinations together. You don't multiply them. You add them up together. So first we had 10 choose one. If he chose one book, we also had 10 choose two for two books. And we keep adding them all the way to 10 choose 10. And as I've mentioned before, you could always like calculate these individually, then add them up. But who would want to do that? That's very tedious. So what we notice is that this kind of looks like you're adding up all the numbers in a row of Pascal's triangle, right? So you're taking the 10th row and you're starting at column number one, not column number zero though, but starting at column number one, and then you increase the column number to add all the numbers, well, the majority of the numbers in row number 10. You have to go now? All right, go ahead then. I'll post the slide, the slideshow and the recording later, so you can like solve the questions on your own. Yep, thanks, Patrick. See you too. Okay, so if you want to express this in like sigma notation, you don't have to know this, and like you don't have to figure out how to convert from a sum to a sigma notation. Don't worry about that part. But if you're curious, it will look like this. So you're starting with 10, and then the number you're incrementing is the bottom number, like the k number, and so you will put that on the bottom. And then you're starting at 1, so you set first k equal to 1, and then the expression that you're substituting into would be 10 choose k, something like that. And say if this k was equal to 0 instead, so say this was 0. Okay, so let's scribble this out. Say that was 0. Then we use that property where this is like equal to a power of 2, right? So this would equal to 2 to exponent n. So 2 to exponent 10. But since we're starting at 1, so k equal to 1, we have to subtract, whoops, not the equal sign. Here we have to subtract 10 choose 0. Right, so we have to subtract that. Because we're not starting at 0, we are starting at 1. So it means 10 choose 0, like you see it's not here. So I have to subtract that from this power. So 2 to exponent 10, that would be 1024. And if you solve for 10 choose 0, oh yeah, I don't think I've showed you this, guys. But 0 factorial is equal to 1. So for all the factorials, you need to have a 1 inside the product. So 0 factorial is actually equal to 1, not 0. I forgot to show you guys that. But just take note of that. Yeah, 0 is always a real number, but yeah, just remember this property. So this is 1024 minus 1. And this will give you 1023. And this is your final answer. Are there any questions about this? I know probably a lot of you have. And go ahead. No questions? Yeah. Anything choose 0. Yes. Perfect. I might as well, yeah, tell you that as well. So any n choose 0 equal to 1, right? So if you want to choose 0 objects out of like any number of objects, there's only one way to do that, right? You don't choose anything. That still counts as one way. Think about it like literally, yeah. So, hey, you don't really have to memorize this property, but it's easy to know, I guess. Just know that 0 factorial is equal to 1. And then using that, you can just figure out this property. Any other questions? No? Okay. There's one more problem I'll let you guys try out. So from the diagram below, how many ways are there to choose 3 balls such that they all lie in the same row? So a row like in the Pascal's triangle, like a horizontal one. No, not a vertical one or not not a diagonal line, just a row. I'll give you guys a few minutes or so to figure this out. And just as a hint, so look at each row. So here's the first row, you have 3 balls. Here you have 4 balls, and it increases by 1. So express like number of combinations in each row as like choose notation and add them together. And you'll figure out that you can simplify that. Well, it depends on which row you have, right? If it was a top one, I can only choose those 3 balls. So if they all have to be in row number 1, there's only one combination. 3, 2, 3, right? If they're in the second row, so I could choose like the first 3, or I could choose the last 3. So that's 2 different combinations already. But that would be 4 choose 3 for a total number of combinations for this row. Yep, you'll guys figure out a pattern. Don't worry about it. Once you figure out the pattern, this is easy peasy. Any answers so far? Just curious. Yeah, go ahead, go ahead. What do you think it is? It is. You have to simplify that though. Mhm. It's there's an expression for that. Like you don't have to like calculate the individual and choose case. Just figure out one and choose case that equals all of that, right? Anyone have an answer so far? One 1480 says Jeffrey. I think that's way too big. Oh, wait, let me see. Uh, I think it is 210. Good job, Eric. Here, well, let's see what it is actually. Let's get a new try. Okay, let's see if it's 210 or 11. Was it 11480. Haven't really tried solving this myself, but let's see. Okay, so as Eric mentioned, you're just adding up a bunch of choose notations, right? So you're looking at, for each row, you're looking at the number of combinations you can choose for 3 balls. So first row has 3 balls, so that's 3 choose 3, and that's obviously 1, but let's keep it like that. The next row has 1 extra ball, so you're choosing 3 balls out of 4 balls, so 4 choose 3. The next row, 5 choose 3, and then you do that all the way. Oops, my ellipses. Last row has 9 balls. So you're adding up from 3 choose 3, sorry, can't speak, all the way to 9 choose 3. That is a lot of balls indeed. But well, you notice that this relates to the hockey stick identity, right? So you had an expression like this. Let me remember what it was. So you had some K choose R, you had N on the top, R over here, and then K over here. So R here remains constant, right? So remember this was like R choose R plus R choose R plus 1 choose R. All the way to N choose R. Right? So you'll notice that this actually looks really similar to this. And you can figure out what N and R are equal to. So N here would be equal to like 9, so the last term here. So N is 9. R is just the bottom number, which is 3. And notice that, remember that this expression is equal to N plus 1 choose R plus 1. Let's do that quickly. So N plus 1 gives you 10. R plus 1 gives you 4. 10 choose 4 is what we're solving for. Right. So we have 10 factorial, close at 0, 4 factorial, times 6 factorial. Right, so this is your final answer, but let's specify this. So 6 factorial cancels out with 10 to get 10 times 9. God, I can't close my zeros. 10 times 9 times 8 times 7. Right. I guess 2 is ready right now, but let's finish up this quickly. And 4 factorial is 4 times 3 times 2 times 1. 3 times 2 times 1. So here, what we can do, we can cancel out 4 with 8 to get 2. 2 can cancel out with this 2. 3 cancel out with 9 to get 3. You're left with 10 times 3 times 7. That will give you 210. This is your final answer. Are there any questions about this?